race where I'm, since the world went crazy. And so this is an LSST project, and which just got accepted in RAS. So I'm currently a postdoc at the University of Pennsylvania. And so today I'm going to talk about that project about deblending galaxies. I want to make a very quick digression because this is kind of an outsider project for me. So I just wanted to quickly tell you the other kind of stuff that I do. So in general, I'm interested in studying dark energy, mostly using weak lensing surveys, and I'm interested in combination with those CMB and exploiting the capacities of different astronomical surveys. And so most of my current work is within the dark energy survey, and now within the year 3, the analysis of the year 3 data. So I work on the analysis combining weak lensing and clustering with consistency test. We have a paper that's in internal review that should be out hopefully maybe this week. Still believe in it. Then I'm working on the cosmic shear analysis with Rogerio and his team. In particular, we're doing that in harmonic space. And then I'm working on combining that DS with CMB data, namely ACT and SB. I'm also working on making forecasts for future experiments, in particular Doux first, which I actually should have changed to Roman, which is the official name now, in combination with the Simons Observatory. And just for fun, last year I did a paper on biostatistics. Okay. Anyway, that's not what I'm going to talk about today. So I'm going to talk about blending and deblending, and a method that we came up with for LSST. So this is the outline of the talk. So I'm going to explain the context and the motivations, then what the blending problem is. Then I'll explain our new method, and in particular, I'll explain what variational autoencoders are and how we simulated simulated the training set. Then I'll show our results, and I'll conclude with and discuss our results and show some perspectives. If my understanding is that there are like astronomers ranging from cosmologies to solar systems science, so I try to make that understandable. If at any point something isn't clear, please feel free to interrupt. Okay, so just the context is that we want to use weak lensing to constrain dark energy. So as a reminder, the idea of weak lensing is that because there is matter and mass between a given source of light and you, then the shape of that source is distorted by the distortion in space-time caused by the mass. And so here we're not looking at the regime where things are strongly distorted, like you can see around that blue circle here. We're looking at it in the weak regime, where, so if you zoom in, you expect galaxies, which are more or less ellipsoids, to be basically slightly tilted. So instead of if the true galaxy, if the galaxy without matter would appear to you like the dashed ellipse here, then because of the distortion, it appears slightly, the ellipse is slightly tilted. So the distortion is like, the idea is that the large-scale structure imprints a coherent distortion of order 1% on galaxies, and by using these distortions, even you can reconstruct the matter density field between you and the sources. And so this is what was done in this paper led by Shiwei Qiang with the DES year 1 data, where the color indicates the density of matter projected over the sky for some redshift bin. And then once we have that field, we can measure its statistical properties, in particular the power spectrum or the 2-point functions, and compare those to theory to extract constraints on cosmological parameters. So weak lensing is a powerful probe both of the geometry and of the growth of structure. So it's an excellent candidate to constrain dark energy, which basically balances the gravitational collapse versus the accelerated expansion of the universe. And on the right, you have an example of the forecast for constraints from LSST. And you see that, so the 3x2 here means the joint analysis of weak lensing and clustering, and that yields that small blue ellipse here, which can be further combined with other probes to make the constraints even tighter, of course. So what is the status of the field? So there are currently three large weak lensing surveys, DES, HSC, and KIDS, pretty much all at the same point, so at the same place. So they have different properties. For instance, so DES has almost 5,000 square degrees in the south sky. In 4 filters, so GRIZ. And we're in the process of analyzing the year 3 data, which now has over 100 million galaxies for weak lensing. Now is actually the rush, so hopefully in the next couple of months, the papers should be out, so stay tuned. And there are, so the 2 other surveys are, so HSC, as I said, which has a much smaller area on the sky, but goes much deeper. That is longer, deeper observations. And so it has compensates for lower, the lower area with a much deeper, with a higher depth, and therefore a higher number density of galaxies, which drives your, this balance drives your the signal to noise ratio. So their year 1 analysis was published last year and this year, and the third one, I'm sorry, the third one is the kilodegree survey, which just presented their KIDS 1000 analysis using their data and BOSS data, and that survey combines optical observations with infrared observations, which means that they're particularly strong with their photometric redshift. All of these surveys are basically trying to constrain those 2 parameters, so S8 or sigma 8, which represent matter fluctuations, and versus the matter density parameter omega m. And this plot represent the constraints from the analysis of year 1 data in DES, where DES is in blue here. Planck data is analyzed here in green, and the combination is somewhere in the middle. So there is definitely, somewhat of a tension between CMB experiments and weak lensing surveys. So it's particularly important to control all the systematic effects in those surveys to understand whether that systematic is an indication of new physics or if it's just an issue with the data. Looking forward, and the next generation, one of the next generation of one of the survey of the next generation, sorry, is going to be LSST at the Vera Rubin Observatory in Chile. And so the project that that I'm going to present is, so this is an LSST project, and we're particularly interested in looking at LSST. So the LSST will have a huge camera of 3.2 gigapixels, and we'll use 6 different filters from the optical to the near infrared, so the UGR-IZY filters. And with respect to in regard of weak lensing, LSST will do a so-called fast wide deep survey, which will be a 10-year survey of about a third of the southern sky, with a depth going to a magnitude of R of 27.5, and the goal is to get of order 10 billion galaxies. So LSST has this, so you can see it on the left, this is the footprint with the number of visits for each patch, because the idea is that LSST will scan the sky 3 times a week. And basically so that we can stack all of these observations and get to the nominal depth after 10 years. And it will do so using a wide field instrument. So this is the focal plane or a schematic of the focal plane with the size of the moon for comparison. And LSST will be somewhere here. Okay, so now, so we're looking at what LSST data may look like. So this is actually an image from HSC, which is actually has a depth, of course, very close to LSST. And so that gives us a good idea of what LSST images will look like. And so there's already, when you see that, an important problem, which is that we're interested in measuring percent level distortions in the shape of all of these galaxies that you can see there. And the problem is that when you go deep, galaxies are blended. That is, they appear as on the same line of sight and basically touch each other. So if you want to measure the elasticity of each of these individual galaxies, that becomes a huge problem. Before explaining how we want to solve that, just another bit of context, which is that in the next decade, or I guess the starting decade, we'll have 2 other weight-cleansing surveys that are space-based, namely the Euclid mission by ESA and NASA's Nancy Grace Roman telescope, or formerly known as WFIRST. It's interesting to think about what you can do with those 3 surveys, because space telescopes offer a higher resolution just because you don't have the atmosphere that's blurring the images, and they can observe in the infrared, which you can do from the ground or apart from the very near infrared. So if you think about combining at catalog level, that is once you have detected the galaxies, if you think about combining the information at that level, then what you get is magnitudes for each galaxies in optical and infrared. And so if you combine those information, you can, for instance, get much better photometric redshifts. And so this is what was done and shown in that plot at the bottom right, where you see photoses inferred from LSST only. So the x-axis is the ground truth, and the y-axis is the what is measured. And what you get then if you combine in, the photometry of WFIRST or Roman, and you see that it gets much like the output or the photoses are much closer to the spectroscopic redshift on the x-axis, and in particular that you have a lot less outliers. Now that's good. You can but there is another step that you can do, which is to think about pixel level joint processing. That is, what can we do if we are to analyze the images directly together? And that offers many possibilities in terms of cross-calibration, detection of galaxies, and as I'm going to show now, deblending. Another, I think an image says 1,000 words, and this is just, I'm going to show, so this is an image of a cluster seen from the ground. So this is DS data, and the same as seen from space. And of course, so here, if you think about deblending galaxies, that is separating all those blobs somehow, having this high resolution, of course, will be of great help. Okay, so now turning to deblending specifically, or I guess the problem is blending, and then the solution is deblending. But why is it an issue? So first of all, for LSST, about half of the galaxies are going to be blended under some definition. Of course, you can you need some definition of blending, like how much they overlap. But it's estimated that about 60% of galaxies are blended for HSC, which is very close to, or as close as we have to LSST. The problem is you could simply just discard all of those galaxies, but that means that you're discarding half of your survey, so that of course decreases your statistical power. But even potentially more importantly, that introduces selection biases, namely that you're excluding galaxies that are in dense regions where there are likely to be more galaxies in the first place, and so they are likely to be blended. Then it's an issue because if you don't address it, then blending will impact both the measurement of shapes, but also of fluxes or colors, and therefore redshifts. And so that blending therefore impacts all of weak lensing science for LSST. Now, why is it difficult? Well, it's difficult because first, it requires modeling the galaxies, which can be done or is typically done with analytic profiles such as Cirsic or Deblender or exponential. But that's obviously only an approximation. Then, as Robert Lupton would say, it's impossible without making assumptions. That is, what we want to do with deblending is basically say in a given pixel, what fraction comes from galaxy A and what fraction comes from galaxy B. And if you don't make any assumption about what galaxy A and B would look like, then it's an impossible inversion problem. And finally, a third and important difficulty is that deblending is tightly or strongly, tied to the detection algorithm. That is, if you don't know that there are several galaxies in the first place, deblending them might be difficult. And so that raises the problem, the question of unrecognized blends. And so this is what's shown here on that plot from that paper, Dawson et al. 2015, where the same pair of galaxies as seen from the Hubble Space Telescope, so in space, and is observed here by HSC. And so if you look at that, if you only have HSC data, then it may look like it's just one galaxy, maybe like elongated, but you would only detect one galaxy when it's actually two. So having space data here is super useful. So there are a number of deblending methods out there, which all of them make assumptions about the shapes of galaxies, and usually they make assumptions about some parametric model. I'm just going to explain what SCARAD is, because that's the pipeline deblender that is being integrated in the LSST pipeline. And so SCARAD only assumes that a given scene, as shown here, is a sum of profiles that are multiplied with amplitudes that represent the spectral energy density of the galaxies. And so the way SCARAD works is that you can make minimal assumption, but still some assumptions, such as the fact that each galaxy is symmetric around a center and has a profile that is monotonically, if that's a word, decreasing from the center to the outskirt of the galaxies. Then they have a way to minimize that and obtain that. But that's still assuming a model. So in the work that I'm going to present now, we have three goals and three problems that we want to try and address. First, we want to make minimal assumption about galaxy morphologies. Then we want to have an algorithm that is fast enough to deal with LSST data. And finally, we'd like to be able to incorporate LSST or Euclid and Roman. I should change that as well. Roman images and process them at the same time as LSST images. Of course, we haven't solved all of these perfectly, but the work that I'm going to show is or tries to address these different problems. So as I said, this is work done with Bastien Arsenault, who's here on the right, after a run at the LSST desk meeting. And the idea is the following. So what we did was to implement and test a new method that is based on true probabilistic convolutional neural networks that share weights. and a schematic of which is shown here. So we have one first neural network here that learns a generative model of isolated galaxy images, and then a second neural network that uses the weights of the generative model from the first network, and a new network here that performs deblending under constraints. I'm going to explain that in greater detail. This allows us to basically include images from multiple bands and multiple instruments as different channels. So here, these are RGB images, but in a neural network, you can have as many channels as you want, not just RGB. So here we'll have actually 10 different channels. And the idea being that the cool thing about such a method is that once trained, it is extremely fast, which is critical given the amount of data that LSST will have to process. So the results that I'm going to show is how we trained and tested this method on simulated images, how we measured the accuracy in terms of the shear and flux recovery statistics, and I'm going to show some initial tests on real data. Okay, so why? So as a reminder, is that working? Yes. So convolutional neural networks work by learning filters that are applied to images, and that can, so that you can learn a wealth of transformation that are required to perform the task at hand. And so they've been extremely powerful, as you know, in classification, segmentation, and other tests. And in addition to using convolutional neural nets, we're going to use generative models, that is, and a specific kind that is, or subcategory of which is a latent variable models. That is where we try to link data X, so here are images, to some latent variables Z that have the nice property of being Gaussian distributed. And so since if you know how to go from X to Z and from Z to X, then you can do both inferences and generate new X's. And so there are two approaches here. The most famous one is probably generative adversarial networks, proposed in 2015. But we're actually going to use another method, which is variational autoencoders. Okay, so what are variational autoencoders? So the idea is that we want to map some input X to some latent variables Z, and then back to the output. So if you do it that way, if you ignore at the moment like all the probabilistic things, you can imagine that this is just some kind of data compression, and then or some encoding, which is why we call that first network the encoder, and that maps X deterministically to Z. And then the decoder does the data decompression, that is, it maps Z back to the data Y. Now, if you do that, what you get is a simple autoencoder. Here we use a variational autoencoder, which is that instead of doing that, instead of having a deterministic mapping, we'll give both X and Z some distributions. And so we can impose that Z be Gaussian distributed. And the neural network, then the decoder neural network, will parameterize the distribution of X given Z. That is, for instance, if this is a Gaussian distribution, then Z may, the decoder can be used to compute, for instance, the mean and the covariance of X given Z. Unfortunately, when we do that, since there is some data compression, we can't just simply invert that property, and so we have to include an encoder network that will approximate the posterior. So if you call that the likelihood, then the encoder would approximate the posterior. And then, so the way to train this neural network is simply by maximizing the marginal probability of X which you can't do. You can't compute that exactly, but we have a lower bound that is given by this expression here that has, and what's important is that it has two terms. One, which is a reconstruction term. So this is measuring the, this is measuring how close x and x prime are. And there's another term here, which is a regularization term that forces the network to have z be Gaussian distributed or over the sample x. And so here, what we're going to, so both the encoder and the decoder are going to be convolutional neural networks with dense layers. So if there are any questions so far, maybe that would be a good time to, otherwise I can just keep going. Okay, I'll just go. Feel free to interrupt at any time. Okay, so as I said before, so we're going to have two steps in this method. In the first step, we implement a traditional variational autoencoder on noisy images of isolated centered galaxies. And so that network, D1, basically learns how to map latent variables onto images of isolated centered galaxies. Then we're going to implement a second neural network that has the exact same architecture. And we're going to use the weights in D1 and use them here and fix them such that D1 only knows how to map latent variables of that represent isolated galaxies back to the images. And now E2 has to do the work of, so the input here is going to be the blended images centered on the target galaxy. And E2, its job is going to be to find the variables Z that best represent the galaxy here at the center. And so in a way, you can consider that this is a constrained deblending, where the model, the generative model that we have trained first, constrains the encoder or the Deblender network here, and it constrains it to recover the codes Z of those variables. And so I'm going to show how we implemented that and then how we validated it, since we're interested in weak lensing, by how accurate the shapes, that is the ellipticities of the galaxies and the fluxes are. Okay, so quickly, so some just if you're interested, these are some details about the implementations. So as I said, the input is always going to be noisy galaxies. And so in the first network, these are isolated galaxies, and in the second network, they are blended scenes. And the output is always going to be centered, noiseless image of the target galaxy. The architecture that we use, so it's a so-called beta variational autoencoder. And I'll just leave those details here in case you're interested later. So now we used a simulated training sample that is made of parametric chromatic galaxies that we generated with the software GalSim, and that are drawn from observations by HST in the Cosmos field. And so for each of these images, we produce an image of the galaxy in the 6 LSST bands using using a 10-year exposures. Actually, yeah, there's. Oh yeah, no, that's right. So that's about 800 observations for each galaxy, but we only use a stack, and then we draw the images of the galaxies also as they would be observed by the Euclid visible and near-infrared instruments. So in total, each image has 6 channels for the 6 LSST filters plus 4 for the Euclid filters. We use fixed PSF using a Kolmogorov model, so that is a PSF, which represent a PSF driven by the turbulences in the atmosphere, and then a MOFAT PSF for Euclid, which doesn't suffer from the atmosphere. The noise is a simple Poisson noise, which is adjusted to the fiducial sky background values. And then we studied the impact of centering the galaxy, which is one hypothesis that we make here. And we studied 3 cases, one where the galaxy is perfectly centered, one where the galaxy is one where we basically include subpixel shifts, that is there's a uniform shift by one or half an LSST pixel. And then the last one that the last decentering technique that we studied is actually applying a peak finder on the images and using just the center that is found by this algorithm as the center of the galaxy. So that allows realistic decentering. So this is what the images, the training sample looks like, where you can see. Sorry, so what's the order? Yeah, those would be the near infrared images, the visible one from Euclid, and then the 6 last ones are the images, the LSST filters. So before moving to the Deblender, these are results that validate the variational autoencoder, which we use as a generative model for the Deblender. And so in the first row of plots, in these ones, I'm showing the input, the ellipticity of the input image or of the target image versus that measured on the output of the Deblender. And so you see that here it's like it's very close. So we do that for E1, E2, and then for the absolute the absolute ellipticity. And then in that last plot, we're showing the mean error. So they divided in the E1, E2 plane. So that is, if you split your data as a function of E1 and E2, as input E1 and E2, then the arrows show at scale the mean output E1 and E2. So these errors are small enough, and so that which allows us to move on. Now I'm going to show this. So this one is also for the generative model, and I'm going to spend a little time explaining those because this is we use these kind of plots to validate the Deblender as well. And so what we did here is the x-axis represents the test sample divided by signal-to-noise ratio, and so whose histogram is or distribution is shown here. And on the y-axis, we have 2 things. So that first main plot shows the distribution of errors in absolute ellipticity, where the line in the middle shows the median, and then the box here and the whiskers show the 1 and 2 sigma percentiles. And finally, that bottom plot here is a zoom on the median, which is also shown here. So basically, the width of those boxes and whiskers tell us what how much the distribution or what is the error on the distribution, and the median tells us if there is a bias. That is, do we recover whether we or not we recover on average the input the true ellipticity. So these are, so in blue we're showing results where we use only LSST filters, that is 6 channels, both in training and testing. And in red, this is when we add the 4 Euclid filters. And you can see that on the ellipticity, especially at low signal to noise, it helps a lot by, especially on the generative model. We have some outliers here, which we couldn't exactly understand where they were coming from, probably because these are outliers in signal to noise. These are very high signal to noise galaxies, and sometimes they may be very broad on the training images. Now this is the same plot, but showing the error on the magnitude in the R band, where you see that Euclid, including Euclid delta, helps a bit, but not as much as for the ellipticities. And the biases in both cases are very small. Okay, so now moving to the Deblender. So I explained how we generated the training sample for the generative model. Now we need to generate blended scenes. And so the way we did that is by randomly picking a number between 1 and 4 for the number of galaxies. Then we simply add them. That is, we do not account for opacity. And here we chose to include the brightest galaxy at the center. There is only a small exclusion area, which is a fraction of the PSF, because if the two galaxies overlap by are closer together than the width of the PSF, then they won't be resolved. And in practice, there's just no way. There's nothing you can do about it. And we introduced or we used a blendedness metric to quantify basically how bad things are, which is given by this number, so computed from by just product of the images. So I centered here represents just the image of the isolated galaxies, that is the target galaxy, and I total here represents the blended scene. And so if B dot is 0, then that is the galaxy is not blended, and B dot is 1, that is the galaxy is completely blended. So this is what the training sample looks like. On the left, you have and some examples. So for each of these 3 columns, the first column represents the noisy input image. The second one represents the output of the Deblender, and the third one represents the target. The blue cross here represents the center of the target galaxy, and the red crosses represent the centers of the other galaxies. And so you see that we have a sample of that is representative somewhat of blends that are that we'll get in LSST, with some galaxies that are not blended, also just to make sure that the Deblender behaves well in these cases, and some very strong blends like here or on that one. Okay, and so then we move on to the analysis of the ellipticity errors. So these plots are now the same, but where we're comparing the ellipticity of the target galaxy from the ellipticity of the output of the Deblender, where the input this time was the blended the blended scene. Okay, and so we're doing different splits. So the first one on the top right is when splitting the galaxies as function of signal to noise ratio, where signal to noise ratio here is measured on the isolated image. So that's actually a conservative measurement of signal to noise ratio, because if it's blended, that would increase the noise. And here on that one in the bottom left, we split the test sample as a function of blendedness from 0 to 0.55. And on that last one, we split the sample as a function of the difference in magnitude between the target galaxy and the closest one. So if at 0, that means that the 2 galaxies are equally bright, and when that increases, that means that the target galaxy is getting brighter than the target galaxy. So in all cases, what we see is that median errors are within 0.01, pretty much stable across signal to noise ratio, and from 10 to 3000, and for and also across blendedness rate. Of course, that's decreasing with the blendiness and for at lower signal to noise ratio. Then the other thing that we see is that as on the generative model itself, using Euclid images helps improve or tighten the distribution of ellipsicities around the truth value, which you by about 30% on the ellipticities, which you can see here to be, which is very well visible here. And then we measured, so on average, ellipticity biases of about 5% and 1% for LSST or LSST plus Euclid. And finally, we measured shear biases by doing something like like the meta-calibration algorithm, that is taking a sample of images, then applying a shear in one direction and in the other direction, and computing the mean of the output ellipticities and comparing that to the shift that we've the shear that we've put in. And we find biases about 4 to 6%, which is actually pretty good for the algorithm before calibration, and also noting that this is measured actually on quite blended images. So reaching this few percent level is actually quite good. This is the same on magnitudes. Again, the medians are pretty stable here, between plus or minus 0.05. Again, with accuracy decreasing as things get more blended. In particular, the fact that this is a negative means that basically the Deblender picks up flux from the neighbor galaxies. And here, again, including Euclid helps, but not as much as for the ellipticities. So these were tests on the perfectly centered images. As I said, we also studied the impact of that hypothesis, and this is what is shown here. So from the most optimistic one to the pretty pessimistic one in green, that is whether we consider just some subpixel shifts in the center of the galaxies, or actually using a detection algorithm, which here is quite simplistic and therefore offers pretty much an upper bound on the spread of the error distributions and the biases. We still find that the median errors are pretty low, but find that but of course so the medians, the biases are pretty low, but the spread of the errors of course increase. The shear biases then degrade to about 8%. And right, but so basically that means that our method is still degrades which is expected, but is still able to deal with realistic decentering of the target galaxy. Then what would be interesting is, of course, to be able to apply that. So all of that to apply that to real data, because all of what I've presented is using simulated images. And so we did some initial tests with that using transfer learning. That is, what we do is we use so the true cosmos images from which we generated our simulations, but this time using the real images instead of parametric fits to them. And we found actually pretty encouraging results. And so let me explain what we did. So here we studied the Euclid plus the LSST plus Euclid case. And so what we do is we first train the VAE and the Deblender on simulated images, and then if we so the results here for the reduced shear bias are shown here in red. Then if we apply that algorithm that has never seen real data, and if we apply it to these real images, then we get highly degraded shear estimates. But then if we retrain those networks, including in the training sample some real images, then we see that these the shear biases are decreased a lot and very quickly. So this is quite encouraging because that means that this opens the way of first training the networks on simulated images, which we can produce. We can produce a lot of them, and then including just a fraction of real images that need to be very well preprocessed, then can lead to very good results. Okay, so let me summarize what I've presented here. So we've used a deep learning model with a variational autoencoder architecture that allows us to come up with a data-driven model for galaxy images, making therefore minimal assumption. And an interesting property of that method is that we do not require any information about the scene apart from the center of the target galaxy. That is, we don't need to know where other galaxies are around it, which is not the case with other Deblenders. And so that opens the way to some iterative procedure where we would target the brightest galaxy, deblend it, remove the model from the image, and then go to the second brightest galaxy and do both the detection and the deblending and so on until you've done all galaxies. We have performed extensive testing of the performances, showing that we have small biases on the LSST and magnitudes, and obtain percent level biases on the LSST and shear when average over sample. And of course, with performances that are strongly tied to the detection or centering algorithm. This is one of the first approach of some pixel level joint processing between LSST and Euclid. And we've shown that doing that, you can get 20 to 30% improvement on blended images by including Euclid data for, when they are available, actually. And finally, we've applied transfer learning and obtained some encouraging results. Just looking slightly ahead of what we have in mind now, one idea is to go to more realistic simulations, that is using background images from HSC and then inject simulated objects there and trying to deblend them. And something else that we are trying is to go fully Bayesian, but on the output ellipticities and magnitudes. And so this is an example here where we show we have a blended scene, and here on that image, so which is the input of the network, and we use as another input an image of the PSF centered on the galaxy that we're targeting. And these Bayesian neural networks allow us to compute posteriors on the ellipticities of those galaxies. And so one example, so the result for that image is shown here. And for a bunch of images, you have the input ellipticities as the output, and the errors also being computed by the network, and we're finding a pretty good agreement, although this is still super preliminary. Thanks for listening, and I'll be happy to answer any questions.
Thank you, Cyrille, for the very interesting talk. We now have time for questions from the audience.
I have a couple of quick questions. Hi. First of all, I mean, what is the threshold to make this? I mean, first of all, congratulations, very impressive work. And what is the threshold to make into the DM pipeline? Is this going to be used for the DM or the desk pipeline?
So quite frankly, I mean, I think this is still quite exploratory, meaning that, I mean, honestly, I think our goal here was to explore methods that use generative models. If you were to use the model as is in the DM pipeline and tell me that W is -3, I wouldn't trust it. Which is like, so I think we're definitely not there yet. One thing that we absolutely need to do, and we're working on it, is to test it on realistic, more realistic images, because here we train on these simple models that still have some symmetry to it. We've had, as I said, we've had some interesting or encouraging results with transfer learning, which are getting closer to the truth. But then something that I didn't say is that to actually do that, you need to make a very clean training sample using the real data. And that's actually quite challenging to do, because you need to actually find isolated galaxies to use as a training sample, and or which is, it's hard to tell. And if you look at that image, the last row, so this is the input image, and you can clearly see that dark dot here, which is a sign that that image was actually masked here to remove some a neighbor to that.
Yeah, you can see it.
Galaxy.
Yeah.
Right. But so I think that's why I think using this method of injecting sources within real images, which is also similar to Balrog in DS, if you're familiar with it. I think that's an interesting avenue, but we clearly need to do that first before integrating into the DM stack. For sure.
Right now, Scarlet is the official Deblender. Is that it?
Yeah, I think so. Now, the interesting thing with Scarlet is that there are you can change what model you use in. Like Scarlet is more like a framework than exactly than a specific Deblender. You can turn on and off assumptions about the galaxies, such as symmetry or monotonicity. But yeah, my understanding is that so far Scarlet is the main Deblender.
I mean, it also is going to be pretty hard to actually combine at the pixel level, right? The data from Euclid, and so this will require a special treatment altogether, right? Let me ask you a final question. I mean, does Euclid cover the entire region of LSST? I should know that, but it doesn't. Right?
No, not completely. I feel like I should know that as well. Here we've assumed that, so we've only looked at galaxies where both are available. But no, I mean, there's a large overlap, like several thousand square degrees, but it's not a complete overlap. So one thing that we could do, is, for instance, train on regions where there is overlap, and
use that information.
Come up with a way, come up with or like to at least tighten the generative models, which constrain the Deblender network. And then applies that to other region. But we didn't tackle that problem here.
So we go deep and we open a Pandora box of problems, basically.
Yep.
Right?
Yep.
Okay, thank you very much.
Thanks.
More questions?
May I?
Yes. Oh, okay.
Go ahead.
Oh, thanks, Basilio. Hi, Cyrille.
Hey,
thanks a lot for accepting the invitation.
Yeah, thanks for the invitation.
And I have a few questions, naive questions. The first one, what is I don't know if we have an idea for LSST and Euclid. We expect about what percentage of blending galaxies in the images?
So that depends. For Euclid, because it's in space, the images are not as blurred, and therefore the blending, and also Euclid is shallower. So blending is not supposed to be that much of an issue for LSST, which is also why it's good to use Euclid images for LSST. But for LSST, yeah, it's a much bigger problem, and about half of LSST galaxies will be blended. Of course, that will after the first year of LSST observations, of course, is not going to be as deep. So, like, you don't have, you know, faint galaxies will not appear, and so and will not be considered as blend, or actually they might be considered unrecognized blends. But yeah, after 10 years, the number to keep in mind is about half of galaxies.
Wow.
So that's a big, yeah. And that's actually, HSC has the exact, like it is dealing with that right now. So I think Scarlet, I think the image that I showed for Scarlet, whoop, oh, going too fast, my computer crashed. Yeah, these are actually HSC simulated image. Maybe that one is actually a real one, but anyway, they developed that working on using HSC data, and with the idea to apply that to LSST.
And this is done. We use the redshift information, or this is done on a plane, just on one plane, or we separate in redshift bins? Because I believe if we have the redshift information, the number will decrease. I hope a lot.
Right. So that's actually, so there. That's a good question. Actually, so the when we do that, you know, the first, so like when we take a picture from the telescope, and at first you don't, so everything is on the same plane, right? So the problem of deblending is that it is tied to detection. So if you cannot detect a galaxy, I mean, you don't have yet its redshift, right? So you need to both be able to say there is a galaxy there and, you know, centered somewhat here, to be able to deblend it and compute its flux and therefore get its redshift. However, one thing that is, just to touch about something about the redshift, is that, so I didn't talk too much about it here, but if you look at that image, which is one filter, so I mean on grayscale, it seems somewhat harder to separate some of the galaxies. So I guess it's not so much such a great example, but imagine, okay, that one, that image in grayscale, that is, if you had just one filter, that makes things much harder than if you have several filters, because if you have several filters, you know, galaxies at different redshifts will have different colors. And so, you know, by doing some kind of linear combination of the different filters, you can isolate one galaxy or the other. So which is why using multiple bands was something we absolutely wanted to do in that project, because that allows you to do that. And Scarlet is actually the first deblender that is able to incorporate images from different filters, right? Because all of these work with single channel images, but the problem is that Scarlet has to makes the assumption that a galaxy is described by a single profile and then just one amplitude per filter. But the problem is that if you look at a real galaxy in different filters, there are color gradients. That is, the galaxy may be, I'm sure I'm going to get that wrong, but maybe bluer at the center and redder outside. And Scarlet wouldn't be able to deal with that. Well, our method, we didn't test it here because it's hard to also simulate, but our method in principle doesn't have that problem because it deals with all the filters and doesn't make assumption about doesn't make the assumption that the profile has to be the same in each band.
Okay. Oh, for example, in LSST, we are working with cluster-mass estimation using weak lensing signal. So this is something that we really have to take care and include the uncertainty given the deblending.
Yeah, especially in clusters, because by definition there are more galaxies there, so they are more likely to be blended. I think. I mean, the problem is that, I mean, you have your cluster, and then what you need to estimate the mass is actually the background galaxies.
Exactly.
But since you detect a lot of the faint galaxies within the cluster and a lot of the faint galaxies in the background ones, then that's getting pretty crowded. I think those images that I used are I mean, they're not completely random. They're quite representative of HSC images, but some of them may be clusters because, where you get a lot of these, a lot of galaxies like that. But yeah, for clusters, that's a problem. And that also, comes back to what I said. Like if you discard all the galaxies that are blended, then you introduce a selection bias because you may be just removing all clusters.
Yeah.
And so that means you're removing all of the dense regions. And so if you're measuring fluctuations of the density field, of course that's going to bias your measurements.
Yeah. Oh, thanks a lot. See.
Thanks, Mariana.
Okay, we had another question.
Okay, if I may, I just wonder what happens in the high signal to noise regime with the shear bias plot you showed. It doesn't seem to improve even after the transfer learning. It's one. It's the one on the shear bias. I think it's one of the last. Yeah,
right,
this
here.
one on this regime. Yes, it's what is going on there that it seems to perform worse than a lower signal to noise.
Yeah, that's true. So I think here the problem may be outliers, and that's actually one problem that you get with deep learning techniques, because they, like a neural network is going to do well on the image that is somewhat the average of your training sample. But here, like high signal to noise galaxies, they may be like very large on the image. They may even be cut by the image borders, and so they might do poorly there. Which is kind of counterintuitive because there is more information. Like the signal is not drowned in noise, but for the neural network it's something unusual, and so it's doing poorly here, which is actually one of the that's an important problem for any deep learning technique. On the other hand, what we might do is something kind of some approach in between, because here we've shown that statistically our method works well, including at low signal to noise. And so you might use some technique like that that on average gets you the right result, and then for the very high signal to noise regime, use some more deterministic method, because then these methods will not fail as a neural net might do.
Yeah, something hybrid. Yeah. Okay. Thank you.
Okay, thanks. We already passed 1 hour. I think we can accommodate a last question. One last question.
I have a last question. So Cyrille, thanks for the talk. It's nice to see your other side, other works that. So my question is about the inputs of the neural network. So where you really input pixel by pixel, what are the inputs and the output? So ellipticity is one of the outputs, for instance. This is a question.
So the network does not. So in this method, the network doesn't know about ellipticity. It doesn't have any constraint that it's trying to recover ellipticity. So the inputs are noisy images. So they're actually 64 by 64 pixels times 10 channels. Like if you use LSST plus Euclid, and same for blended scenes. And the output is, since we're using simulations, is the noiseless version of the central galaxy. But yeah, we've actually before reaching that architecture, we've actually had to play with, like, we tried simpler ones, of course, at first, and it would give us some blobs that were okay, but getting the ellipticities right was actually more complicated, because getting the magnitude right is quite easy, because it's the magnitude is basically, the log of the flux, or which is just the sum of the pixels. But yeah, getting the ellipticities to some reasonable agreement was actually quite challenging.
Right. So you measure the ellipticity on the output.
Yeah, exactly. Yeah, yeah, and we apply the same. Even so, the to make sure that we're not biasing ourselves, we also measure. We use the same measurement code on both the input or the target image and the output, just because, I mean, it's a pixelized version of the real image. So, you know, even if we like Gaussian tells you what the shear of an object is, but to make sure that we're not biasing ourselves there, we use the same measurement. But that's also, so, you know, I mean, here we're actually performing deblending. That is, we're separating each galaxy from the other, and then so that you can run your traditional measurement. And while the approach that we're working on, that I just mentioned here, is to actually not deblend and just directly get a measurement of the ellipticity and maybe the fluxes directly from the blended image.
Okay.
Okay.
Thank you, Cyrille. Very nice work.
Thanks, Rogerio. Thanks.
Okay. Thank you, everyone. This presentation will be available on our website, linea.com.br, and on LIneA's YouTube channel. For the next week's webinar, we will have Emir Uzerbegovic from the University of Hertfordshire. He will talk about galaxy morphology using principal components. Thank you, everyone, for attending, and a special thanks to Cyrille. And
Thanks,
everyone, have a great day and see you next week.
Bye-bye.
Bye, thanks.